Part 2, Flat Earth, Song and Water.
Laboratory was led by Russi Taliarkin.
Late January 2001, late afternoon. Trying to look for signals. Now started pressing the button on our high-speed scope and just kept our fingers crossed and said, let's see what comes out. The very first time around, it started clicking. That was extremely exciting.
The clicking was the sound of a detector recording neutrons, the telltale sign of nuclear fusion. At the first attempt, it seemed that Russi Taliarkin had done what nobody else had been able to do: make his star in a jar hot enough for nuclear fusion. The key to his triumph was a brilliant idea. In sonoluminescence, vapor molecules trapped inside the bubble smash together, heat up, and give off a flash of light. But Russi Taliarkin realized that too many molecules might actually cushion the bubble's collapse, and so the reaction wouldn't be violent enough for fusion. So he started with smaller bubbles that contained fewer vapor molecules, which he thought would now be forced together with much more energy when the bubble collapsed, creating a much hotter core inside his star in a jar, a core that would finally be hot enough for fusion. And in January 2001, it worked, and he detected neutrons.
Elated is not the right word. Ecstatic may not be the right word either. I mean, it was difficult to sleep soundly at night that day onwards.
Russi Taliarkin knew that his breakthrough would be big news. But he also knew that cold fusion had been big news before it was comprehensively discredited. So over the next few months, he checked his results and confirmed them with other tests. He measured the neutrons again and again, but the results were always the same. And only then was he convinced about the scale of his discovery.
Nuclear fusion is a major finding. Some people think that it may be worthy of a Nobel Prize. It would be nice if it were, but I don't keep dreaming about it. If it happens, so be it.
And so the dream of a shortcut to nuclear fusion and the prospect of unlimited clean energy was alive again. But that was just the beginning of the story. For such a huge breakthrough to be scientifically accepted, the results first had to be published. Russi Taliarkin aimed high and sent his paper to one of the most prestigious scientific journals in the world, Science magazine. Its editor, Don Kennedy, remembered just what had happened with cold fusion.
With the overhang of cold fusion, one would naturally be a little hesitant about a fusion claim that looks improbable. But you shouldn't ignore something because it's scary. I think the experiments were very well done. I found them convincing. And so, although we recognized that this was going to be controversial, we really thought it was a very interesting finding.
Science magazine sought out the opinions of other experts in the field. And although their comments were not all favourable, Don Kennedy decided that on balance, this remarkable paper was good enough to print.
We felt really comfortable about going on with the paper, comfortable in the sense that it was solid work from a very good laboratory by good people, and it would have to then endure the test.
So on the 8th of March 2002, Russi Talyakin received the endorsement of America's most prestigious scientific journal, and his fusion results were published in Science magazine, and immediately ran into a storm of criticism. That serious flaws had somehow been overlooked.
Things in the article didn't seem quite right.
Fusion found this paper unready for publication.
Less than.
Ultimately, many scientists felt the paper should never have been published at all.
Claims require extraordinary proof.
Fusion research is a heavily contested field, both because there are reputations to be made and because the amount of federal dollars spent on it is quite large, and people want their share of that research support. So don't ever expect this to be a peaceful domain in science. It's not going to be.
The criticism focused on one crucial issue, the same issue that cold fusion had foundered on: neutron detection. The best way to check if fusion was happening was to detect neutrons, the tiny particles that are given off when atoms fuse together. But there was one major complicating factor. Russi Talyakin was also using neutrons in his experiment. The small bubbles that led to his breakthrough were created with a device called a pulse neutron generator, which fired out over 1 million neutrons a second. And sorting out these background neutrons from any created by a small fusion experiment, although possible, was no easy task. Some scientists suspected that Russi Talyakin's fusion neutrons could in fact be coming from his own neutron generator, bouncing around the room and then entering the neutron detector, where they were mistaken for evidence of fusion. Russi Talyakin had an answer. He had conducted several control experiments to rule out the influence of background neutrons. But even in Oak Ridge, there was a conflict over his work. The management of the laboratory was sufficiently concerned about Russi Talyakin's fusion claim to ask someone else to double-check it.
And now we'll count for another 2 minutes and see how many we got.
They called in Mike Saltmarsh, an expert neutron hunter with over 30 years' experience of neutron detection and fusion.
42,043 neutrons. 42884. The reason I was asked to look at it is actually I hate to sound immodest, but I'm rather a good experimental physicist. And I do bring a background in neutron detection.
Mike Saltmarsh's task was to work out whether the neutrons detected could indeed be from fusion or were simply background neutrons from the neutron generator.
There is always a background, some of it due to natural background radiation. In the case of this experiment, there was an additional enormous background from the neutron generator itself, which was producing 1 million neutrons a second that were going all over the place. And consequently, any neutron detector has to be able to sort out whether the neutrons it's seeing are from that or from something else.
The way to do it was to run the experiment again in Russi Talyakin's laboratory, where Mike Saltmarsh could measure the neutron background, take it into account, and then